is mainly his research is mainly focused on stochastic models of emergence of pathogenic strains and early disease dynamics. And today he's going to be presenting some of his work in the area. Jacob, the floor is yours.
Cool, thank you very much, Fatima, and thanks. Thank you for inviting me to speak at this. Really excited to be giving talks at these kind of seminars. It's something I haven't been able to do much. I think that's probably the same for a lot of us. So yeah, really happy to be talking today. So the title of my talk is Stochastic Invasion of Variants of Concern. So we've all kind of been living and breathing this, so we hopefully all know what variants of concern are with respect to COVID, and the effectiveness of border control strategies at keeping those things out, but sort of talk a bit more about that as the presentation goes on. Yeah, so I've obviously, as Fatima says, I'm from the University of Manchester, but I've also just put this Juniper Consortium here as well. So for people that maybe haven't heard of it, the Juniper Consortium was a group of universities, I think only in England, set up during the pandemic. And the idea was to kind of pool their resources and expertise to kind of come up with better models for sort of prediction and during the pandemic. So it was set up, I think, in 2020. But if people are kind of interested about epidemic modeling or anything that I talk about in this presentation, I would definitely recommend checking out Juniper Consortium. I'll maybe drop a link to them in the chat when I'm finished. But yeah, it's definitely very worth checking out. Oops. Okay, it's not letting me. Hold on, sorry, it's not letting me go on to the next slide. Okay, there we go. Yeah, so as I say, we probably all know what variants of concern are. So in the SARS-CoV-2 pandemic, variants of concern have been the sort of persistent nuisance and pose a real challenge for infection control. And there's two main reasons for this. They can either be more transmissible between hosts, and we saw this a lot with the kind of alpha and delta strains, or they may be able to escape host immunity, and this has kind of been more of an issue with Omicron. And this immunity can be acquired either through a vaccination program or through previously having been infected with a different strain. And when variants of concern emerge, governments typically sort of rush to place restrictions on international travel in an attempt to keep the variant out. And as we've maybe seen, and maybe we might have kind of some intuition about this, conventional border control strategies are known to be really leaky. And interestingly, we kind of saw this with Omicron as well. There was some pushback when travel restrictions were placed mostly by European countries on South Africa. There was some kind of pushback against that, which I think was completely fair. But I've just listed a few papers that kind of talk a little bit more about this. So there's a very sort of famous Deirdre Hollingsworth paper on travel restrictions from 2006. I'm going to talk a little bit more during this presentation about the Scully, Atomba and Wallinger paper about this, because this is sort of the foundation of some of the work that I've been doing. And then this one as well, I thought was interesting, about estimating the failure risk of quarantine strategies in Australia and New Zealand, which we kind of typically regard as having had very good border control strategies. And that is true, but I think this paper sort of highlights how many sort of, I guess you might call them breakthrough infections or sort of infections that have made it through quarantine. And I think that emphasizes the point that kind of shifts the problem further down the line. So it's not just that they have good border controls in Australia and New Zealand, but they've had really good contact tracing and other kind of measures. So that's also something that we're going to talk a little bit more about today. So the main idea for this presentation and for my work more generally is, given that we know border controls are leaky, they're not a kind of be all and end all solution. Perhaps a better way of assessing their effectiveness is kind of in thinking about how long they delay the introduction of a variant of concern. How much time do you buy by imposing border restrictions early in the development of a new VOC? So that's kind of going to be what I'm talking about today. So I'll go back to the Scalia, Tomba, and Wallinger paper that I mentioned, because they provide a really good, simple mathematical intuition for why border controls are not necessarily always effective. And so they just use a really simple model where they assume that importations of cases follow a Poisson process with an intensity lambda of t. So this can depend on time. And then the time to first successful importation follows an exponential distribution. So it's given by this expression here. We just integrate the intensity and do 1 minus e to the minus integral of lambda t. So that's kind of simple expression for the time to successful importation. But if we now suppose that each immigrating infected case has a probability q, that its lineage goes extinct, then we get an expression that depends on q. So what I mean by lineage going extinct is either they don't infect anyone, or maybe they infect 1 or 2 people, but the outbreak kind of ends after that. It just fizzles out. So we get this new expression that depends on q. So we just multiply the integrated intensity by 1 minus q. And that's good. So we can do some things with that. So if we, for example, assume that the intensity is increasing exponentially, which is a reasonable assumption to make if there's a sort of exponentially growing pandemic outside of your country or outside of your community, or whatever it happens to be. And we let tau of q be the median time of introduction given control probability q. Then the extra median time to introduction that you get, if q is our kind of baseline, if q equals 0 is our kind of baseline, the extra time that we buy is this tau q minus tau naught. And it has this expression here on the right-hand side where TD is the doubling time of the invading strain. So how long does it take for the number of cases to double? So if we just denote this interval, this tau q minus tau 0 by delta of tau and rearrange, then we obtain an expression for the level of control needed in order to achieve a given delay. So this is kind of their simple intuition, and it provides us a nice expression for the control probability. So we can plot that for different realistic parameters. And then the trouble is that what this shows us is that we need really, really effective controls to achieve even a slight delay in having imported cases. So for COVID in the early days, sort of early 2020, people were estimating a doubling time of between 3 and 5 days. So if we kind of look between the 3 and 5 days, we can sort of see that to achieve a one day delay of introduction, we would maybe need like a 20% control probability. So 20% of the cases we're effectively blocking. But to achieve, say, a 7-day delay, we're looking at this orange curve. That's going to be like 80% of cases needed to be caught at the border. And to achieve anything more than 7 days, I mean, we're really looking at stopping almost all cases from coming through. So this is not a great result, right? We would need to have essentially perfect border control measures to keep it out indefinitely. So I think that's quite a good place to start. And it gives us a simple intuition. But what we don't do in this model is we don't consider any disease dynamics, right? We don't consider what happens to cases once they enter a country. We just see how many cases do enter. So we can extend this model a little bit by actually considering disease dynamics, and we do this in a simple kind of either a single type branching process, or you could think about it as an SIR framework. So due to the pandemic, maybe a lot more people know what an SIR model is than they would have done previously, but I'll kind of quickly go through it now. So we essentially split the entire population into people that are susceptible, infectious, or recovered. And then we just have a simple model that means that people are infected by people that are infectious and move to the I category. And then they do that with a transmission rate beta. And once they're infectious, they recover at a rate gamma. And I've also put here a SEIR model. So we can also include a latent period, which is a bit more relevant for COVID, because we know that people are asymptomatic and don't transmit for a certain period at the start of their infection. Also, again, people might know what R0 is, but I'll just briefly define it, although we're probably all pretty used to hearing about R on the news. But this is defined as the number of secondary infections arising from a single infected case. And that's when the population is fully susceptible. So we think about defining R at the start of the epidemic. And it's kind of measure of how infectious a disease is. So in order to model this stochastically, we can use a single type branching process that kind of captures these dynamics. So we assume in the kind of simplest case that each infectious case produces one additional infectious case per infection event. So you're only ever infecting one person at a time. And you do this after a time that is exponentially distributed with rates beta plus gamma. And so for this process, we can define a very simple probability generating function that's given by this. And so we're kind of looking at the exponents of S for each expression. So the first expression, the first sort of bit of it, we've got a beta times S squared, which says that you infect one other person. And so after that infection event, there are two infectious people, you and the person you've just infected. And then we've got a plus gamma times S to the 0 term, which is if you recover, there are then 0 people resulting from that event because you've recovered, so you're no longer infectious and you haven't infected anyone else. So that's kind of how we get this, this generating function. And what this allows us to do is it allows us to define a probability Q of T, this time depending on time, that the lineage of a single infected case has become extinct by time T. So not only do we have the probability that they're kind of caught at the border, if you like, at time T equals 0, we now have we can now track that probability after they enter and begin to infect other people. So slightly skate over the detail here, but we can solve the Kolmogorov equations or the master equation for this process. And that allows us to recover the probability that there is a positive number of cases entering from outside at time T. And it's essentially analogous to the previous expression, except this time we have Q depending on time. So that's quite nice. For not that much extra work, we've got a bit more information. And so this now slightly looks a little bit better. So it's a slightly different graph, but we're looking at the probability of extinction after 100 days. So the probability that you have 0 cases after 100 days. And if we look at, say, reducing transmission by about 40%, now we're looking for an R naught of 1.5, sort of maybe 95% chance that you have 0 cases after 100 days. So this is already quite a lot better than what we had before. Whereas for these higher R naughts, maybe you've got like a 50-55% chance of still having cases after 100 days. So this is already looking a little bit better. And also, thanks to kind of having this branching process set up, we can kind of add in some extra features that might make our model a little bit more realistic. So we can explicitly account for superspreading events. So we don't have to assume only one infection per infection event. We can assume these kind of clustered infections. And the standard way to do that is instead of just having an S squared term, we can replace this with the probability generating function of a negative binomial distribution. So this gives us some cluster of cases, which gives us a slightly different, but not that much more complicated generating function. And you can notice as well that if we replace K with -1, after a bit of simplification, you recover exactly the same model that we had previously. So in a sense, this is slightly more general. Also in the single type framework, we can derive solutions with time-dependent transmission and recovery rates. That's really useful because if transmission depends on time, then we can model things perhaps like a lockdown where transmission slows down quite a lot. So that's a very useful thing to be able to do. And then just like the Scalia-Tomba and Wallinger paper, we can also have non-constant immigration rate. So maybe there's a border control where they say, okay, we're going to close the borders, no more flights. You know, we can model that using this model. So that's another useful thing to be able to do. And all of this kind of just adds a bit more realism, which kind of improves on the sort of simple but intuitive results from the Scalia-Tomba paper. So that's a useful thing to do. So just as an example of this, what happens if we introduce superspreading events? So k equals -1, the top one, this is kind of the vanilla model where we don't have superspreading. And then below we have k is equal to 0.1, which was some people were kind of estimating for COVID, for that to be the sort of appropriate choice of k. And what you can see is that if we're plotting the probability of extinction of a single lineage of cases of COVID, when you have superspreading events, you actually have a higher probability of extinction. That might seem counterintuitive, but what it means is that for the same value of R, in order to kind of balance the average, you have a small number of cases that are producing lots of secondary cases, but then the majority of your cases are producing much fewer cases. So the idea is that kind of most people are not transmitting as much, but when you do have an outbreak, it has the potential to be much more explosive. So that's why you have an increased probability of extinction. That's the sort of intuition there. But this is just another thing that we can do. But then I'll sort of come on to the main topic of my work, and this is really the big thing that we can do. The one thing that the Scalia-Tomba paper or the single type model doesn't consider at all is heterogeneity, and in particular heterogeneous immunity. So it completely ignores the fact that some people may have previously been infected and have some immunity, and it also ignores the fact that we've had a vaccination program. So these two things make an enormous difference. So we can extend our model fairly straightforwardly to be able to include this. And instead of having a single type model, we can have a multi-type model. And so what we do is we divide the population into 4 types or types at birth for people that are sort of more familiar with the branching process language. So we get 4 types based on a person's immunity status. So one type if someone hasn't been vaccinated or previously been infected, one type for people that have been vaccinated but not infected, one type for people that have been infected but not vaccinated, and then one type for people that have been both infected and vaccinated. So we get 4 types for a reasonably simple model. And the way that this works in our model, the way that we model this, is we just sort of scale the force of infection or the sort of transmissibility of people based on who they're infecting. So if you're infecting somebody that's double vaccinated and had COVID before, you're less likely to infect them than somebody that's completely susceptible. So we just see this scaling. Instead of beta, we now have beta j is equal to fj times psi j times beta, where fj is the proportion of type j individuals, and psi j is their kind of relative susceptibility based on their vaccination or immunity status. We also add an exposed class. So I mentioned before having an SEIR type model. This is slightly more realistic for COVID. So we end up with 8 types. So we get 4 types of E and 4 types of I to end up with 8 types. And again, we can quite straightforwardly get a probability generating function for this process. So if each person spends an exponential length of time in compartment I, we get a sort of reasonably simple offspring distribution, or a reasonably simple probability generating function. And now this is super useful because this essentially defines the entire process. So we can quite straightforwardly recover the mean number of cases at type T from this process. And this just involves us kind of doing a simple integral where the matrix omega is just taken from the partial derivatives of our offspring distribution. And then we have to remember the fact that at each infection event, we sort of make this assumption that rather than me infecting one person, I infect one person and I create a copy of myself, and then I effectively recover. So it's a slightly kind of notational point, but that's where we get this -1 from as well. But this is kind of standard to anyone that's sort of familiar with the branching process literature. So we can recover the mean, which is really useful. And we can also recover the variance, which is a little bit more technical, a little bit more involved, but still possible to do analytically. And we do this for an outbreak that begins with no cases and is then seeded by imported cases of type I. So we assume that at the start of the epidemic, if we think about maybe Omicron, we assume that there's no Omicron cases in the country, and then sort of drip by drip, there are going to be sort of cases of each type coming into the country from externally. So we can obtain the variance for the whole process. So we do it for each type I, and then we just sum all of those variances up to get the variance of the total number of cases at time t. So those are two kind of useful things to get. But what do we really want to do with this model? We really want to kind of think about the time that different control strategies buy you. That was kind of what we were initially thinking about. And one way of thinking about that is we can think about the point in this epidemic where instead of using a stochastic model, we can approximate with a deterministic model. And the reason that's a good thing to think about is if we're using a deterministic model, then we can be sure that our outbreak is growing exponentially, right? There's no sort of stochastic extinction going on. So this is maybe a good idea, a good thing to think about to try and answer this question. And so when this becomes the case, we call this point T star. And we look at the point where this constant of variation, which is the standard deviation divided by the mean, reaches a limit so that it's approximately constant over time. And what that means is if you've got an epidemic that's growing, your sort of confidence interval around that mean is only growing proportionately with the mean. So you can sort of conclude as well that it's sort of sufficiently bounded away from zero. So understanding when this happens turns out to be quite a useful thing to do. So I've done some plots of that for various values of R0. So if you consider an R0 of 2, the sort of purple dashed line, so the orange line is this coefficient of variation, the standard deviation divided by the mean. And I just plot in purple where we say that this is approximately constant over time. And so for an R of 2, this kind of happens after 96 days. So this, is a reasonable amount of time to prepare other measures like contact tracing and stuff like that. Whereas for a much higher R of 4, I should say 4 instead of 4.41, it's only about 18 days. So really for like a much higher R0, you really don't buy yourself very much time necessarily by having kind of smaller importation rate. Yes, and there's something else. So I was also going to say about this, that we can also think of a reduced R0 as being the impact of non-pharmaceutical interventions. So as well as having border controls, if there's a new variant of concern out there and it enters the country, people might also think about having a lockdown. So you might interpret this as reducing R from being 4 to say 2 or maybe even lower than that. So this T star is kind of sort of becomes the object of study. And we don't just want a kind of central estimate for T star, we also want to know about the distribution and the variation around T star. So here what we do is we assume that for all T greater than or equal to T star, we're assuming that we can approximate with a deterministic model, which means that our outbreak is going to be growing exponentially. So the log of the mean, the log number of cases, this log Z of T, should be growing, it should be growing like RT, where R is the growth rate. And then we have some variation around this growth rate that we model using a standard Brownian motion. So if we let Z star be the time at which the number of cases, sorry, if we let z star be the number of cases at time t star, then the time taken for log zt to reach log z star is given by an inverse Gaussian distribution. So an inverse Gaussian distribution is kind of standard, is the sort of standard hitting time for a Brownian motion. So we use an inverse Gaussian distribution, and we estimate the variance of log of z using the delta method. So we just take the second derivative and use that to estimate the variance. So this actually kind of gets us a little bit closer to what we were looking for. So if we take this r is equal to 2 and plot this inverse Gaussian with these with these parameters, what we see is a distribution that is very highly skewed. So the mean, as we said before, was 96 days, but really this mean is kind of in the tail of the distribution, and kind of many more sort of with much higher probability, we're going to be in this kind of low time to successful establishment, low time to exponential growth. So many more of these are kind of below 20 or below 40 days. So that's kind of worth considering as well in this, and sort of one thing that we're going to be trying to do with this work as well is kind of looking at some of the higher order moments. So maybe looking at the kurtosis as well and seeing what that tells us about the distribution. But yeah, so this kind of gives us a little bit of what we want. And if we plot this for different values of R0, so we've got R0 from 2 up to 4, and I plot this on a log scale so that we can kind of see the full tail of the distribution. We see we get this kind of nice relationship where the R for an R of 2, we have a distribution with a sort of very high variance, and we sort of have this kind of monotonic relationship with R0, whereas R0 increases, we get a sort of lower time to introduction, and this kind of aligns with our intuition, right? We expect a very highly transmissible variant to be much faster at getting into a country. So again, it's kind of slightly distorted because it's on the log scale, but again, the mean for this R is equals to 2 is 96 days to exponential growth, and the mean for this R of 4 is equal to 18 days for exponential growth. So it's quite a substantial difference for different values of R0. So I would say that's probably the main thrust of the work that I've been doing on that. But there's a couple of other things that we can add to make it a little bit more realistic. So one thing that we can do is slightly relax this assumption about having cases enter the country one by one. And we could instead have kind of clustered importations. So to do this makes our model a little bit more realistic. And unfortunately, it's kind of not really possible to sort of have a negative binomial process. That kind of work has not really been done, and I'm not necessarily sure that it can be done. So, but this is kind of the thing that we would want to do. How we get around it is we still have cases coming in according to a Poisson distribution, but then we use the superspreading model that we had before. So remember, in the superspreading model, we replaced our standard offspring distribution with a negative binomial. And we can do this in the same way with imported cases. So if we sort of interpret imported cases as maybe, instead of maybe being like planes or cars or boats or something like that, and we sort of don't count them, but we say that they have a negative binomial number of secondary cases, then this will kind of give us clusters of cases that then go on to seed outbreaks in different places. So it's a slightly cheating way of doing it, but it seems to work. so we just do that. And that kind of adds a little bit of realism as well. And then we just need to be super careful that we're not counting these cases when we actually calculate the mean and variance of the overall process. So I'll just kind of come on to like the sort of current work, sort of how we're developing this model and the future direction of some of this work. So These results can be used with kind of reasonable parameter choices. That's kind of the approach that we've been taking so far. But ultimately, we're also going to be interested in fitting this model to data, right? So we'll want to be kind of using data from of importation from different countries. And there's two ways that we can do this. So obviously, we can obtain data about the sort of time taken to exponential growth. So we can sort of look at what time the epidemic sort of truly takes off in a country. We have to be a little bit careful about how we interpret that and exactly how we define that, because it makes sort of sense. It makes sense in a kind of modeling sense where we're talking about the difference between using a stochastic and deterministic model. But if I'm looking at data for the number of cases in a country, at what point can I say this is now growing exponentially, there's no chance of extinction? It's a little bit hard to interpret that from data. But one thing we can do is we can look at the probability of extinction. So we can look at sort of local outbreaks and sort of what proportion of those just kind of fizzle out without being kind of reseeded by immigration. And for that, we also can obtain a likelihood because we have an expression for the probability of extinction, both in the single type and the multi-type scenario. So that's probably more like what the how we'll actually be doing that. And then this kind of final point is that really an ultimate goal would be to repeat this analysis for time-dependent transmission rates. So I talked about that in the single type case, where we had sort of a beta of t that can represent, I don't know, whether you have lockdowns or maybe you have increased mask wearing or some kind of other non-pharmaceutical interventions, or you could even include contact tracing in that. Unfortunately, in the multi-type case, this is difficult, and as far as I know, hasn't been done. And this is something I was trying to do at the start of my PhD in a slightly different context, but didn't get anywhere with. So I think it's just hard. But that would be an ultimate goal. So we kind of might look at doing that again. And one way that we can simplify it is if we can't do it for sort of general time-dependent rates, we might sort of choose piecewise constant transmission rates and see if that gets you anything. So if you do that, what you end up with is your sort of Kolmogorov or master equations end up being a PDE instead of an ODE, and it's in general more difficult to solve. But maybe there are sort of some clever techniques that we can use to solve that. So that would be one thing to do. But yes, so I think I'm ending slightly early, but that's all I had to say. So thank you everyone for listening. And yeah, let me know if you have any questions. I've put my email there in case there isn't time for questions, or you had a question like maybe after the event. Do feel free to email me. But yeah, thanks.
Thanks, Jacob. That was very interesting.
Thank you.
Very challenging to do a lot of the stuff that you were talking about there. Any questions? You can either, oh, someone has their hand up.
Hi, can you hear me?
Yeah.
Sorry, I'll go ahead. Hi, Jay. Thanks for that. That was really interesting. I actually have a few questions. I've actually been working on some coronavirus stuff myself. Particularly interested in this idea of heterogeneous transmission, so the negative binomial distribution. So just trying to understand what it is that you're saying. One of the things you're really interested in is the time until the epidemic can be modeled well by a deterministic model.
Yeah. And
so my question is, does your model, I know you might have said this already, does your model allow for, or does your analysis allow for the case where you've got super spreading going on from the imported cases?
Yes, so that's kind of one thing that we're trying to do at the moment. So we've got a model where you have super spreading sort of amongst the resident population, and then we're sort of trying to kind of get around not being able to model clustered importations by having importations that produce a negative binomial distributed number of cases. So it's a slight cheat, but yes, we are able to do that.
So I didn't quite understand your branching process equations. Could you go back and just clarify something for me? It's a
yes, sure. Is it this slide?
It's where you said you got k minus 1, k equals -1.
Ah, yeah, sure.
And anytime I parameterize a negative binomial distribution, k is strictly positive. So have you changed that somehow?
No, again, this is also a slight cheat. So you are right, k should always be positive. But it's really just an observation that if you, so I'm sort of not trying to say that it's a negative binomial distribution with k equals -1. It's more just the observation that because the negative binomial distribution has this generating function, if you literally just substitute k into this, k equals -1 into this, you recover the initial dynamics without superspreading.
I understand.
But yes, no, that is completely correct. It's a slight abuse of notation.
Okay. And if you have your parameterized your negative binomial, you're basically saying that your expectation is 1, right? That's the expected value that you set to 1 there in that notation.
Yeah.
So is one of the extensions you're looking at is trying to put a reproduction number in there in the negative binomial, or have I got things kind of the wrong way around? So what happens if you don't have 1 there?
Yes. So essentially, the reproduction number is kind of already in here. So actually, I think I've slightly written this wrong, where I've written beta twice on the top. But you've got beta times s, which gives you 1 additional case, and then you've got a negative binomial distribution with mean 1. So essentially, on average, you're going to get effectively 2 new cases, one the infector and one the infectee. So you'll get 2 every time. And then this represents 1 infection event. So that infector can then go on to infect other people. And over that infector's lifetime, the average number of cases they'll produce before they recover will be R. Yeah.
Okay. I see. It's a slightly different perspective to what I'm used to. Okay.
Yes.
That's cool. How would you go about fitting this model to data?
Yes, that is a current sort of problem that we're having. But essentially, what we're looking at, so it's kind of we get an expression for this extinction probability, and the way that we can do that, the way that we can use that is we get a likelihood based on that extinction probability, and then we can fit that to the proportion of cases that go extinct locally. So it's a little bit difficult to interpret, but you sort of essentially look at there's kind of some literature on like stuttering chains, these sort of imported cases that maybe like you look for where only a few extra cases have been produced and then they die out. But obviously that's kind of quite high fidelity or high level data that we're looking at. You know, we sort of really need to be able to see when that's happening. And you've also got the problem that potentially more cases are being imported as that is happening. So it might be that one lineage goes extinct, but you don't see it in the data because additional cases are being imported. So it's that is potentially going to be a bit tricky, but we're gonna try. So hopefully there might be some data in the UK that does that, and we've got some colleagues in Denmark that might have some data on that. But initially we're sort of hoping to like publish this just as a sort of theoretical model, and then be able to kind of fit it to data as well.
So what you're saying is it's really, really detailed context tracing information that you need to actually fit this model. That's what you're saying.
Yes, potentially. I mean, unless there's also some question about whether we can sort of interpret from data when the time at which an epidemic takes off. So if we can kind of have some simple measure of when of when we decide that that's the case, then we can also fit to that. But again, that has its own problems too.
Sure.
And are you going to be assuming that? Yeah, sorry, no, that was going to be my question about the data. Are you going to be assuming that there is just that one variant that is rampant in the population? How do you know, or do you need to differentiate between the variants that you're?
Yes, no, that's a good question as well. So in the sort of simplest model, we assume that there's a kind of a wild type or a resident strain, but actually that could be many strains, right? So if we were thinking about Omicron, the resident strain could be Delta or Alpha or Beta or anything else that's kind of swimming around. And we sort of lump all of those together and compare them with Omicron. And again, sort of needing this sort of higher fidelity data, we would probably get around that by only looking at cases that are connected to travel, at least in the initial stages. So connected to travel that have been identified, where, you know, so that the initial case has been identified as an Omicron or new variant of concern. So we'd sort of get around it that way, which is not perfect either. But that's kind of one way that we would look at it.
And you can get access to that kind of data?
Yeah, so often there's this kind of line list data, or in sort of in the context of new variants of concern, often there is that sort of data available. Not necessarily in all countries, but sometimes it is.
Yeah, I don't know if you can access that type of data in Ireland.
Yeah, I'm not really sure. We've mainly been looking at the UK, and as I say, we've got some colleagues in Denmark that do that as well.
Yeah, that's cool. One unrelated questions to the data, but you said that the model assumes, or the initial models assumed, a homogeneous population, right? And you're introducing heterogeneity by saying that immunity is heterogeneous.
Yeah.
I've looked at some SIR models before, and the way they normally go about introducing heterogeneity is like introducing some sort of matrix that represents mixing in the population.
Yeah.
And my question is just going to be like, does introducing heterogeneous immunity kind of do the same, basically the same thing? Yes,
effectively it does. So we're sort of, we can think of it as well as like, usually heterogeneity is kind of thought of in terms of like imposing a risk structure. And so we do that as well. I slightly skated over the detail, but we've got a sort of omega ij, and this is kind of the, so usually in those models it would be a deterministic model, but we can sort of do a stochastic equivalent, and it kind of comes straight out of the offspring distribution. So that's quite nice. I mean, the really good thing about using branching processes is that you can get a lot of analytic expressions that sort of just come out of the offspring distribution. So it's quite a nice framework for doing this.
That's all from me. Any other questions? No.
Well, I could maybe ask another one, if that's all right.
Yeah,
cool.
Yeah. So just to clarify, kind of what the story that you're picking out of this is it fair to say that what your analysis tells us is that it kind of doesn't matter how strict your border controls are, but that if the rate at which the disease will spread within the population once it gets in is too high, it's going to take hold. Is that kind of the story? Yeah,
that's definitely part of it. I mean, I think essentially the way we've been coming at this is that the narrative sort of exists that border controls don't work. That's sort of a way that lots of people have thought about border controls, because you can't stop it from coming in indefinitely. And so what we want to do is kind of, instead of thinking about it in that kind of binary, does it or doesn't it work? We want to think about it in terms of how much time it buys you. And so the simple intuition tells you that it doesn't buy you very much time, therefore it doesn't work. But we want to say that by incorporating the disease dynamics, incorporating a potentially infectious, like more infectious or not that much more infectious variants, by sort of adding in all these kind of other elements that make the model a bit more realistic, you can improve on that. I mean, if you remember sort of back on these slides, you know, I mean, these results are terrible. Like, they tell you shouldn't do border controls. Like, this is all awful. And what we kind of end up with is for an R0 of 2, say, where you have some MPIs and potentially some controls on borders as well. Okay, so this is a very skewed distribution, but you could be looking at somewhere between 20 and 40 days, say. for introduction, or potentially a distribution with a very long tail. So this is kind of not saying, oh, you shouldn't do border controls. This is saying you should think about it as buying you time, in which time you can sort of, I mean, in the very early days of the pandemic, you know, there wouldn't have been nearly enough contact tracing, not nearly enough testing capacity, all these other kind of things. It's sort of buying you time to ramp those measures up. That's sort of what we hope the take-home message from this modeling is.
So you're defining basically the amount of time that you should have the border controls for.
This is with the amount of time with a given set of border controls, that you will get until you have exponential growth in your country, essentially. So you can also vary this for different border controls. You can vary it for different border controls and different levels of animals.
Oh, okay, I see.
So there's a sort of equivalent to this picture where you have different levels of border controls, and you kind of see the same thing. You sort of see this monotonic relationship with stricter border controls. Yeah.
Any other questions? Nope. Just double check that there are no hands up. Nope, that's it. Thanks, Jacob. That was really interesting.
Cool. Thank you so much. Thanks for having me.
Thanks, everyone.
Cool. Thank you. Thanks. Nice to meet you as well.
Nice to meet you too.
Thanks, Jacob.
Cheers. Thank you. Thanks, everyone.